Well, I need to apologise that Helen isn't here, but she normally chairs all these meetings, and she's had to go off to an urgent meeting, so I'm basically going to do that for you this afternoon. I'm very pleased to introduce Martin Bonsoir from Biamp Systems, who's going to give us a very interesting presentation called An Exploration of Network Audio Protocols. So, Martin, over to you.
Thank you very much.
Thank you.
Hello, good afternoon. Don't have to introduce myself. I have already been, which is good. We've got a little time, so I will try to go through it as quickly as possible, but please do feel free to interrupt me as many times as you want with questions. I do have some sort of agenda they will try to keep up to, but I have no problems with deviating if the common interest takes us somewhere else. So what we are trying to see in the next 45 minutes is to try to understand why we even bother with network audio, what advantages or disadvantages does it take us, what problems are encountered when you decide to move away from maybe standard digital or analog audio into a networked environment. We will see how AVB, CobraNet, and Dante solve those problems and how they differ in their solutions. Once we see that, we will also talk a little bit about ISCEx. We cover a little bit on layers and routing because by experience, by that moment, people tend to be confused about those two. And then we will open it to questions. Make sense? So, first point, any idea why would we even bother with network audio? Why do people spend time and effort and money in trying to develop this? Indeed, by and large, mostly it's costs. And if you try to break that down, network audio came to replace, by and large, analog audio in some circumstances. As we were discussing, there are circumstances where analog audio is still by far the best solution. But it does try to solve a number of problems. The first one is that, by and large, analog audio forces us to use one cable per channel and only one direction. Now, of course, network audio does allow, in every single case that we will look at, multiple channels per cable and in both directions per cable. That already makes the wiring a lot simpler. The other thing about analog audio is that it's point-to-point. If I want to send audio from A to B, I need a cable from A to B. If I want from B to C, I need a cable again, and a cable again, and very quickly things become very complicated. Network audio, by definition, it allows audio from any point in the network to any point in the network, regardless of how that network is wired. It supports a whole number of different topologies, and indeed, for it to be qualified as network audio, it must support all of these topologies. As soon as you've got things wired, I can go and send audio from this node to this node without any problem, without having to run a cable between them. So that's another huge advantage when we come to deploy it on site. The other big advantage is that if you, like me, have spent most of their life working with analog audio, you will know that your car is full of adapters and a soldering iron. And doesn't matter what, you will never have all of the connectors that you will need. Network audio, by definition, uses a single connector, as long as it's copper. You can argue that you need a different one when using fiber, but it does make installation an awful lot faster, a lot simpler, easier to troubleshoot. And the other common improvement of network audio over analog is the analog is subject to degradation. As soon as you start running it a few meters, then you are going to have signal degradation for a number of different reasons. Now, network audio suffers from degradation as well, because it's an electrical signal going down a cable, or it's a bit of light going down some glass. But because it's digital, it can be rebuilt without adding any more noise. Rebuilding analog audio without adding noise, it's not that simple. Doing it digitally, it's very, very simple indeed. So those are the very basic reasons why network audio tends to become an interesting proposition in some cases. Make sense? So for the subject of what we're going to look at today, I have chosen a limited number of technologies. And there's a reason why the talk is called network audio and not digital audio. And the first one, why these protocols have been chosen to be investigated are because they all support uncompressed signal. I consider all of us working in the professional audio, we don't do compressed signal. YouTube does compressed signal. That's good for them, but not for this. They have to allow full bandwidth, full uncompressed digital audio. The other one is that they must do low latency. One of the huge advantages of analog audio is they suffer from almost no latency at all. As soon as you start jumping into digital, latency does become a big problem. In professional audio, latency is just not acceptable beyond certain limits. So everything that we're going to be talking today, they all support low latency. And the last qualifying criteria to be included in today's talk is that they must allow interoperability between different manufacturers. There are network digital protocols out there, but they belong to one manufacturer, and for very valid reasons of their own, they don't allow other manufacturers to implement it. As such, I have removed them from this talk because they are very brand specific. All of the ones that we included here, for one means or another, any manufacturer is able to go, pay the license, or download implementation papers, and they can include it in their products. Make sense? Now, at this point, I would like to make a little disclosure to make it easier. I do work for a company that sells all three of those protocols. We sell other ones as well. And the reason why I say that is because every time I have given this talk, I have been accused of being biased towards one specific protocol. So I sell all three. I really don't care which one you think is the best one, because it's the same to me. But every time I do it, I've been told, oh, you like this one better, you like that one better. Hopefully, I have removed all of that, especially because every time it's a different one. But the way that I have organized it this time is chronologically. So we'll see the oldest one, then the second one, and the third one. And maybe that gets the bias out of the equation. So the first one we're going to be looking at is CobraNet. CobraNet was developed, about 20-odd years by a very, very smart group of people working for Peak Audio. Peak Audio was later purchased by a company, Cirrus Logic, which are currently the owners of CobraNet technology. If you want to implement CobraNet technology, you go to Cirrus Logic. They say, yes, of course, it's my pleasure. Here is your bill. They will sell you the software and the hardware necessary to implement CobraNet. The other protocol we're going to be talking about is Dante. Dante is a technology developed around 2006, so it's coming up to about 10 years now in the market. Certainly a lot more popular in the last few. They belong to a company based in Australia called Audinate. They developed, just like Cirrus Logic with CobraNet. If you want to implement Dante, you go to Audinate, you have a chat with them, and then they will sell you the software and the hardware necessary to implement it. And the last one we're going to be talking about is what is started to become known in the market as AVB, Audio Video Bridging. Then the task group behind it changed the name to TSN, Time-Sensitive Networks. Now most people tend to call it deterministic Ethernet. That's certainly the name that I prefer. The bottom line is that it's not a technology that belongs to one specific company. Rather, it's an umbrella name for a bunch of IEEE standards. Do you all know what IEEE is? Largest electronic association in the world. Last time I checked, they have 420,000 members around the world. It's a lot of them. They develop a whole number of standards. All of the ones in AVP TSN do come as approved IEEE standards. So, when I started this talk, I mentioned about how analog audio tends to be one channel per cable. If you wanted to have multiple channels, that's when multi-core cables come into the equation. So capacity on the three protocols that we are talking about, CobraNet allows, in theory, on a single 100 megabits per second cable, 64 channels one way, 64 channels the other way, on a single 100 megabits per second cable. You could potentially get more on a gigabit, but CobraNet is not a gigabit technology. Sadly, one of the things that happens when Peak Audio was purchased by Cirrus Logic is that by and large all development ceased. There were some attempts to do gigabit CobraNet, then even a proof of concept, it never really worked. So you can get that, however, on a single module. The largest module they send, the CM1, CobraNet Module 1, the marketing department spent a lot of time thinking about that one. They allow 32 channels in, 32 channels out. They also sell 16 by 16 and 8 by 8 solutions. So that's pretty much the largest you're going to get in one node. Dante, that came about 10 years later. It allows you, theoretically, in a lab environment, 512 by 512 on a single gigabit link. They do also sell a whole number of different implementations. By far, the most popular is the Brooklyn 2 bridge, the one that you will find in most implementations in the market. And that allows 64 channels in, 64 channels out on a single node. By and large, lastly, AVB TSM, which by and large doesn't really have limits because it works in a different manner. Is how big is your connection? Depends. Commercially, which is what I'm interested in, what can I go to the shops and buy and implement tomorrow? The largest one is 420 in by 420 out. Yeah? Capacity makes sense? So, having solved that, having solved the problem of routing, we've got all of that. We have already agreed that you can send audio from any place to the other place. Now, network audio suffers from one major problem, and that is that Ethernet networks were not designed to send audio. Ethernet networks were designed to send email, data. They don't care the order in which the packets arrive. They don't care about the latency in which the packets arrive. They just care that the packets do arrive. In audio, we really much care the order in which they arrive. We very much care about the timing, the latency that they arrive. And if some of them got dropped, I don't want to listen to that speech again. I'd rather drop them. So that's a different change. And that is what people call deterministic, because what is available in normal Ethernet networks is really not necessarily a good thing for us. And indeed, when we are using most of the Ethernet-based technologies, the order by which the data arrives to us, it doesn't matter. Because when we're trying to watch a YouTube video, we are happy to wait for the spinning wheel to buffer all the data until all the packets arrive, and then they get displayed in the right order. In real-time audio, that's not acceptable. So, all of the different protocols have to find ways to achieve that deterministic delivery. The first thing they need to do that is to agree on synchronization. And that is because in a network, you are going to have different nodes with different clocks. And it doesn't matter what manufacturers tell you, and I represent a manufacturer, clocks will go adrift. There's no two clocks which are precisely the same throughout all the time. They will end up being at different times. And when you're reading data, that timestamp is critical. Because if I think I'm in one time here, and I send audio to the other guy that's in a different time, he's going to be reading something completely different. And that's what distortion and jitter comes into the equation. So you must make sure that all of the nodes in a network, they are synchronized as precisely as you possibly can. CobraNet solves that problem by getting all of the nodes, as soon as they connect to the network, to enumerate themselves. They send a multicast packet to the whole network and saying, hello, I'm here, I'm Martin. Then they all have a bit of a chat between them, and they decide on a conductor. That conductor, from then on, will start sending bit packets about 750 times a second with its own internal clock. And it's the job of all other devices in the network to offset their own clocks so they match the incoming bit packet. And that happens 750 times a second to make sure that all of the nodes are as close to each other as possible. Incidentally, another job of the conductor is to send reservation packets. They get sent about once a second. They include all manners of other information as to who's got transmitting rights and what bundle is going to where. This other sort of admin that happens there. But by and large, CobraNet solves the problem of synchronization by sending very, very frequent packets to the network with a timestamp. That's why most network people hate it, because they don't like to see tons of packets. Dante, 10 years later, did implement it in a slightly more elegant way. And they did so based on an IEEE standard, the 1588 2002 edition, also known as PTP, Precision Time Protocol, which is based on NTP, which perhaps you may be a bit more familiar. And the way it works, again, all devices connect to the network, they enumerate, they say who they are, and then they have a little chat amongst themselves, and they decide on a clock master. That clock master is now in charge of keeping time, and everyone else will slave to it. But rather than sending 750 packets a second down the network, what it does is about once per second, the master will send one packet to the slave. Now the slave knows what time that packet arrived. Shortly thereafter, the master sends a second packet with an exact, precise timestamp of when the first sync message left. Now the slave knows times 2 and times 1. The slave responds and sends a delay request at time T3, so then he knows what time T3 is, and the master replies with the time that he received that second message. So now the slave knows that if it subtracts T1 to T2, knows the delay plus the offset between the two clocks. And if it subtracts T3 to T4, it knows the delay minus the offset. You put it the other side and you know the offset. So rather than using 750 packets to solve the problem, you use a couple. And now both clocks will be synchronized because they know exactly how adrift they are from each other and they can adjust their own clocks. That's 1588, and that's how Dante solves it. Of course, because it's the IEEE, and they get bored when they're at homes, their wives don't want them there, they send them back out, and they decided to do 1588 version 2008, which is the one used by ABB TSN. Remember, AudiNet came out in 2006, so they're using an older version. The people from TSN decided that 2008, it has a number of improvements. There are certain things, there are packets in the version 1 and PTP, if they are sent on UDP over IP, can only support version 4, so 2008 supports version 6. There is support for other networks, including wireless ones. There is support for other media. There's a whole number of improvements. The timing mechanism is allowed to happen up to 10 times a second, so that synchronization is a lot tighter. There's a whole number of agreements, but TSN agreed on using what is known as AO2.1AS, IEEE AO2.1AS, done by the AO2.1 committee, which you may recognize is the Ethernet committee, the people that do the standard for Ethernet. And that's a subset of the 1588 2008. They removed a whole number of options to make it less open. And they known it as generalized precision time protocol. And the big difference, in my opinion, to the implementation is that now the switches play the same game as well. It's no longer just about the end nodes. Now, the cloud in itself is also part of the negotiation for clock master, and they indeed, now the switches can be the master or slaves. The big advantage of this is that now every single node in a network is keeping time, not just the endpoints. So then if you lose a master, reconvergence is way faster. You can also expand a lot more because now you no longer have multiple nodes in the middle which are completely oblivious of time, and then you have to wait for the timeout between one node to the other one to respond before you start realizing that you've got a problem. The downside of that is that in order to implement ABB TSN, you must have a switch which does support AL2.1as. If it doesn't, you're going nowhere. It won't work. Make sense? That's synchronization. Now, the second problem that all of these protocols need to resolve is that of bandwidth. Again, in the analog world, I have one cable that is intended to send one channel from A to B. I have the entirety of the copper to myself. I hopefully know that copper is good enough to send my audio, and I haven't got a problem. Now, that's easy to do when you have the entirety of the network to yourself, and your channel count is not going to exceed the capacity of the network. The cruel reality in the real world is that networks are not like that. Networks are full of data. And now you start running into the problem that you have more data than when you can potentially send. And you have to start making decisions. Again, different protocols look at this problem in different ways. CobraNet does something which is known as best effort, which is a nice marketing twist to saying it does nothing at all about it. CobraNet sends the audio and he hopes it gets to the other end. There is nothing in the protocol that ensures any sort of defense against not having the available bandwidth. As installer, it does mean that then it's your job to do that. Indeed, Cirrus Logic Peak Audio did provide a tool which is now about 20 years out of date, but it does CobraCat, which allows you to try to work out how much bandwidth you're going to have from A to B and trying to make sure. But by and large, you must certainly be protecting it with VLANs, i.e. trying to keep it away from other traffic, or you have to have a dedicated network and make sure that you're not going to go at any one, especially uplinks, if when the problem occurs, above what the network can cope. Dante also uses best effort, but in a more elegant way, because it's newer. And he uses using something known as quality of service. And specifically, they do use DCSP, div service, one of the flavors of quality of service, which in a way, it allows traffic to have a flag about how important they are. So the idea is that Dante traffic will have some sort of identification that allows them priority when they arrive to the different switches in the network over other traffic. Is considered best effort because there's no guarantee. If I have one door and two of my guests arrive at the same time with top priority, I'm still going to have to drop one of them. But if I have one door and two arrive, one has high priority, the other one has low priority, then of course the one with high priority will get through without delay. That's what is known as best effort. Because there's no guarantee, again, recommendation by manufacturers and by indeed Ordinate in certain circumstances is that you protect it with VLANs. Sorry, I forgot the other point about div service. Of course, for it to work, your switch needs to support it. There is a commonly perceived concept that Dante runs on any switch, and yes, it will work, but for any of these to function, you must have a switch that, as per Ordinate, supports 4 strict priority queues with divserv. Otherwise, this data gets added to the traffic, gets to the switch says, no idea what you're talking about, you go into the same queue as everyone else. So you must remember that is a requirement. As soon as you go, the recommendation is above 32 channels on a 100 megabits per second network. So you must remember that. If not, create your own VLAN or your own dedicated network, and again, make sure that the bandwidth is there. If you fail to do so, everything must probably is working beautifully, and then suddenly the whole office receives an email with a nice link to the latest cute kitten video on YouTube, and your whole audio starts going down because the whole bandwidth is gone. ABB TSN, again, that's something different. And it is something which is defined by clause 35 on AO2.1q. It used to be known as QAT. Then they put it in 2011 into all one packet, which is known as Stream Reservation Protocol. And what it does is, before any node is allowed to send any audio, the entirety of the network ensures that the bandwidth required for that particular audio exists. Once that bandwidth has been guaranteed, they create a bridge, hence the original name of audio-video bridging, which is now solid there and reserved for that traffic. No other traffic is able to use that particular bandwidth on those particular ports. It's creating a per port basis. It guarantees the delivery. It forces you to have a switch that supports AO2.1q AT. If a switch doesn't support AO2.1q AT, the node will say, the bandwidth is not reserved, I'm not even going to attempt. You get no audio at all. Yes? The beauty of that, of course, is now you don't longer have to care about VLANs or the specific networks, because it is the job of the network to guarantee that traffic. Once it tells you the audio from A to B goes, audio from A to B will go always, no matter what. The other thing the ABB TSN does, which CobraNet and Dante don't, mostly because it's all part of the same AO2.1q 2011, clause 34 used to be QAV back in my days, is something known as traffic shaping. If you, like me, have no social life and you start looking at packets in a network, how they work, they will tend to bunch up. They do. That's the way switches work, that's the way network goes. That makes for a highly inefficient use of bandwidth, because you're going to have tons of packets all putting one next to each other and then big gaps in between. What AO2.1QAV does is that it spaces them up very nicely. And it schedules the way that they are going to be done. It does it very fast because it's done in silicon, so there's no latency, no penalty in latency being paid on that one. But it allows you to, A, manage the network a lot nicer, and also guarantee in the middle of your data space for non-priority data. So you're protecting both your high-priority data, in our case audio, but also all of the YouTube videos that the office downloaded. They now have a very deterministic spaces in which that data can be queued and sent. That's very new. Again, it requires a switch that supports AO2.1QAV, otherwise it won't work, but it does make a huge amount of difference to the way the traffic is sent, and hence the channel count goes through the roof. You're using much more efficiently. Make sense? Questions? Am I boring you too much? Good, let's carry on then. Now, as I mentioned earlier, those are the three protocols I cover in this talk, which actually haven't got much left, nice and on time. There are protocols people normally know. There are certainly QLAN, Ravine, and LiveWire, perhaps are the most commonly known. They are perfectly valid solutions. They work, all three work very well, but their respective owners do not license them. Hence, I didn't include them. But they do have, and certainly the AES has been working in a means of getting those protocols to start interoperate. AES looked into it. They realized that LiveWire, Ravenna, and QLAN, they're all based on best effort diff-serve, quality of service. They mostly use 1588 synchronization protocol. So then you could go down to a lower common denominator, which would allow them to interoperate. And that's what AES67 is. It's an interoperability standard. It's not a full solution. Oops. And that's what most people get a bit confused. AES67, as it stands, does not specify how devices will enumerate on the network. It doesn't specify exactly what the different options in which the session will be initiated, and there's no full agreement which one is the best and the least best. So it's not a replacement to LiveWire, Ravenna, QLAN, Dante, AVP, or CobraNet. It is something that will allow mostly those based on 1588 and diff-serve to share channels. But you're not going to get, at this point in time, AES might change their mind, you're not going to get an AES-only interface. You're going to get a Dante interface that supports AES67. You're going to have a LiveWire interface that supports AES67. There's actually even provision, whether that will ever happen or not, I don't know, but there's a provision to also do an AVP implementation that also supports AES67. Does that make sense? Is that clear how the difference one to the others? Now, the other comment that is made a lot, and I have been doing my best to not mention it here, is layers. There is an awful lot of talk when any of these protocols come into the equation about this is layer 2, this is layer 3, this is layer 11. I thought it was important the first time I gave the talk to cover it because I perceive there being a lot of misinformation on this one. And it's not misinformation that's unfair. There is some wrong assumptions that people are allowed to take based on the information that is given. The information given is correct. To make sure that we are all on the same boat, which layer belongs, it all comes from the OSI model. The OSI model is a conceptual model of a communication protocol. They go through different layers. Layer 1 is the physical one. Layer 2 is what is known the data. Layer 3 is the network, and then they go higher up towards the actual application. It is a model. That means that how things work in reality and how things are as good as an acoustic model it is to reality. There are some technologies, MPLS, is that layer 2, is it layer 3? Is L2TP, is that layer 2 or layer 3? There are a lot of changes. There are other models, they split it into 9 layers. There is another model that splits it all into 11 layers. So it's just a model. But it's true, there is one big difference between layer 2 and layer 3. Well, what the protocols were, and that really is in addressing. Layer 2 devices and protocols use a MAC address. That's a unique identifier between Martin and Lola, so then they know who they are. That gets stamped from manufacturer. You can do MAC spoofing, but by and large, people shouldn't have duplicates and shouldn't change that. While layer 3 devices is what is known as IP, Internet Protocol, so they use IP addressing. It's a logical addressing. You could have the same address being used for multiple devices. What logical addressing allows, in theory, is to do routing. And that's what the most of the miscommunication and misassumptions occur, because people will immediately associate layer 3 with routable. And it seems to be that in the world in network audio, being able to route is the holy grail. Not so fast, though, because one of the principles of networks is that you will have different segments, broadcast domains, subnets, call it as you want. Each one has its own broadcast and multicast data. And the job of the router, which is a layer 3 device, is to block that data from one network to the other one. Because if it didn't do that, then every single traffic from every single network will go to every single other network. The internet will collapse immediately. Any network will collapse immediately. Multicast traffic, by default, does not go over a router. Even more so when you're talking about professional low latency audio. In real world, routers are connected by interlinks. Those interlinks may be as long from here to the US. The latency there is way, way beyond what we would consider wise. And there has to be a mechanism to manage it. So, because of that, layer 3 is not equal to routable. I encountered this weekly in my job. Oh, you support layer 3, can you route it? No, you cannot. It doesn't mean that because you are, you can. For very, very good reasons, because you are in different broadcast domain, you're in network circuits, and 1588 uses multicast. The clocking mechanism uses multicast. It will not go across a router. If you don't have synchronization, the entire thing collapses, as I showed you earlier. So, yes, it's theoretically possible. It can be done in lab. There are 1588 does specify what they call boundary clocks, clocks with 2 inputs. So they're able to take the clocking synchronization from one end and transfer it to a different subnet and keep sync between the two. It's a terribly difficult thing to implement in real life. There isn't one available commercially now that supports Dante, CobraNet, or ABB. It has been done in labs. I have seen it working in a lab in a very, very, very controlled environment. There is no solution, you can go and purchase it. So that still remains an option, but not something that you can do. And that's the bit that I wanted to mention. Questions? Silence?
Where does AES 70 now start fitting this?
AES 70 is someone cleverer than me mentioned it, is the MIDI of world. It's control, not audio. It doesn't mean that it is. There's a whole argument. AVB is called audio-video bridging. Neither here nor there. Is data being sent from left and right. Was contained, shouldn't matter, provided it's delivered quickly enough. There's nothing that will stop people putting audio inside the payload in AES 70, but indeed that's what the intention was. Yes?
Just a general question.
Yes.
If you were able to look into your crystal ball for a minute.
Yes.
In, say, 5, 10, 20 years' time. I know it's a completely...
It's a very large crystal ball.
It's a very hypothetical question. But do you see the evolution of this technology, if you like, in a Darwinian theory? Do you see it reducing down to 1, 2, or just the current number of 3 main protocols for this technology, or do you see it condensing even further down to just like one unitary system, or is it just such a big commercial market that inherently it must have more than one protocol available? Where do you see this developing?
I'm not sure. I can say how do I see it. I can certainly say how I would want it to be. I really would prefer And that's why I certainly support efforts like ISCEx or AVB TSN. I would like things to be, we're just talking about network audio, and everything talks to everything, and don't necessarily care about, well, this one is LiveWire, this one is QLAN, or this one is Dante. As a user, I just want to connect my Cat5 here, my Cat5 there, and it will work. That's what I think is a much better solution. Having said that, that means the companies that develop the technologies make a lot less money, and they do have commercial interest. And as such, then I'm not sure if the industry will cease to have multiple solutions. One of the things that I find extremely interesting, and certainly one of the reasons why I became interested in this particular site, is because coming from the analog world, certainly I started my career in coiling XLRs on a stage. So the addition of AVB TSN makes a big shift in the thinking for us in the audio industry. We're very, very used to having solutions like CobraNet or solutions like Dante, which were developed by audio companies for the audio industry. They meet our needs very specifically. They provide a solution for our needs very specifically. But we're not a very large industry, are we? We wanted to call audio-video bridging because we like the audiovisual industry, but really the people that develop it couldn't care less about. They are thinking about other industries. They are thinking about automotive industries, the industrial control. That's really what they do and what the big money is. So it's interesting to see how we, as a traditionally insular and at the same time parasite industry, adapt to playing with the big boys. Are we going to be willing to go that route, or are we going to continue with saying, yes, no, but I'm so special, I need something different? And that may be true. They may be, yes, we do a solution that requires low latency support for 96 kilohertz, support for something that really can only be provided by some technology, some company in our industry, because it's the only one that can understand it. I don't know which one. I would like to go into something that works for everyone. Whether that's possible or not, I really don't know.
Is there a kind of common front end to the AVB side of things? Because one of the things I think that people like about Dante is everyone knows you go to the Dante controller, you learn it, you know it, you patch it, that's it.
Yes.
Does the same concept exist yet in AVB?
No. And that's indeed one of the reasons why Dante is far more popular than AVB TSN on this point, and probably for the foreseeable future. Ordinate is the company behind Dante. Unlike Cirrus Logic, they actually take an interest on the technology. They have a marketing department, they do training sessions, they have videos, they are behind that technology because it's what pays the mortgages. So they have the big difference. CobraNet does not pay Cirrus Logic mortgages. It's about this much of the revenue. Dante is almost all the revenue from Ordinate, so they have an interest, so they have that. AVB, because it doesn't really belong to anyone. There really isn't someone driving it as such. There is the Avenue Alliance. The Avenue Alliance has been around for quite some time, most of it with absolutely no funding whatsoever. It has received some better funding of late. They have been doing some stuff, but they don't produce a controller. There is a number of different controllers. There are at least 3 which are available in the market. There are some more which are on beta versions from different multi, but no one really maintains it and makes it available. The same for ISCEx. ISCEx, they now have the Media Network Alliance, which they formed to try to promote it. It is funded by a couple of the players that they have perhaps the biggest interest in seeing that happens. That, again, that's different. The biggest founding members for Avenue, actually none of them sells AVB at this point, which explains the lack of funding for so long. But yes, they are very different to what the job the Ordinate will do for Dante.
Ladies and gentlemen, we have time for a couple more questions, so please feel free to ask.
Or maybe we don't have.
Okay.
I'm happy if we all decide to finish it.
Yes. Well, Martin, I think you're going to come back into the exhibition marquee.
I will indeed. And
So, if you would like to ask Martin any sort of questions on a one-to-one basis, he will be very happy to do so. So, on behalf of the ISCE, I would like to formally thank Martin for his presentation. I hope you found it very interesting this afternoon, ladies and gentlemen. Also, now I would like to thank all the delegates for attending today. I hope you found all three presentations interesting. I also would like to thank the presenters that took their time to come in and talk to us today. I think it's been very informative. I will thank Helen Goddard for organising them. She's not here now, but I think Helen deserves a round of applause for organising all the seminars today. Finally, I would like to thank Cunning's Recordings for providing the public address system for the seminars, the exhibition, the networking dinner we had last night. They come every year. They offer all their services to us free of charge, and they work extremely hard. So please thank Cunning's Recordings for this.